Okay, now we're going to look at color vision theory. So we already look at how the color is actually perceived by human being, how, what is the structure that is involved in color vision perception. And also we look at the colors properties. Okay, now we want to move on to the color vision theory. So basically, how does these colors are being actually, have been explained to explain the color vision. Okay, so there were researchers that were conducted on to explain how the color vision perception is actually happens in the eye. Okay, so there are two main theories that is actually well known. Okay, accepted by the the researchers back then. Okay, one is trichromatic color theory and another one is open process color theory. So basically these two theory, they agree that yes, they agree that there are three types of cones that is available in the, in the retina layer. And that cones are the one responsible, for how the color vision to be perceived. But how the color are being processed by these three types of cones is differ from from trichromatic color theory and also open process color theory. So we're going to look at one by one and how that is actually different from one to another one. Okay, so the first one is, as I mentioned, is trichromatic color theory. Okay, it is proposed by Thomas Young and refined by Hermann von Helmholtz. Okay, so these are the two people behind this trichromatic color theory. They suggest that color vision is based on the combined activity of these three types of cones. Okay, so each type of cone is more sensitive to a different range of wavelengths. Short cones are more sensitive to short wavelengths, okay, corresponding roughly to the blue light, while M cones are more sensitive to medium wavelengths, which we perceive as green light, and long cones are more sensitive to long wavelengths associated with red light. So these are the three types of cones based on trichromatic theory. Okay, they say that we have three types of cones and each cone is sensitive to different wavelength light. Okay, the S cone is sensitive to shorter, M cone is to the medium wavelength, while L cone is sensitive to longer wavelength, which is more like a reddish color. Perception of color arises from the varying levels of stimulation of these three types of cones. For example, when we see yellow light, it stimulates, the cones, okay, like medium cones and also long cones, but not as cones. Okay, so our brain interprets this combination of cone activity as the yellow color. Okay, so basically this trichromatic color theory tells that there are three types of cones, and that cones are L cones, M cones, and S cones. Okay, that's how it is actually interpreting the or perceiving the colors. Okay, and the next one is open color theory. So open color theory, okay, it is actually suggested by Evel Herring. Okay, so he also agreed that, okay, there are three types of cones that is available in the eye that is responsible for perceiving colors. But he is not agreeing with what trichromatic theory has actually mentioned. He said that yes, there are three types of cones, but these cones, each cones have like but opposing pair colors. Okay, so perception of color is governed by a system of opposing pairs of colors. Okay, so color is processed by bipolar hue channels referred to as the, okay, they have like in one cone, they have like a channel. Okay, the first cone, the first type of cone contains of red-green channels. Okay, the second cone is blue-yellow channels, and the third one is white-black channels. Okay, so there are three types of cones which is actually doing different job. Okay, so when the receptors in eyes are stimulated by red light, they become less sensitive to green light and vice versa. And this opponent process color theory, they work like a seesaw. If let's say a color like red is actually seen by patient, a red color bottle, for example, water bottle is placed in front of the eye. So what will happen is the light will go into the eyes. Okay, the object's image light goes into the eye and then it will hit the retina. And then when it hits the retina, this long wavelength cone, sorry, this red-green channels cone will actually absorb the light. Okay, so when red light fall on the retina, and then it is detected by the retina to be a red color. So these red-green channels will get activated and they will absorb this red color, red light. So once it absorbs the red light, what will happen is the red channels will get activated while these green channel get deactivated. So that's how it works. So if let's say you place a green color bottle in front of a patient's eye, okay, a person's eye, what will happen is if let's say green color is actually, seen by patient, the light goes into the eye and then it will activate the red green channel cones. And then what will happen is the green one will get excited. Okay, the green one will get activated and the red one will get deactivated. So that's why it is always, explained that this opponent color theory, it works in like a seesaw. Okay, when one is get activated, another one get deactivated. When another one get activated, this one get deactivated. So it's like a seesaw effect. When one side goes up or get activated and other go down as they are deactivated. So this explains why you might see an after image of a green if you stare at red object for a while. Okay, that means when you are looking, just try look at a random red color wall for a long period. Okay, what you will see is when you shift your eye, go somewhere else, you will see like a green shades. Because their explanation, Abel Herring explained that because that cone contains red and green channels. Okay, so that's why, when it is actually, the red get deactivated when it is shift, right? There will be at one point of time that this will actually, be in the same level. Okay, so that's the time that you will have an after image of green color. Okay, the same explains for blue, yellow channels also. When you see blue, blue get activated. When you see yellow, yellow get activated. Okay, and then when you look at, some plain wall or something, you will see the residual colors. And also we have a third channel, which is known to be the white-black channel. Okay, or it is known to help in brightness. It refers to the perception of brightness rather than color. Okay, it is more to how bright is the color or how dim is the color. So when we see something very bright, okay, like white color, it suppresses our perception of darkness and vice versa. If let's say we look at dark for a long period, so it might suppress, it suppresses our perception in the bright. So this means that when one color in the pair is stimulated, the other is inhibited. So it works like a seesaw. Okay, thank you.